Okay.
So I've found this statement by the Canadian Advisory Committee on SARS in 2003 to be very powerful. We are constantly a short flight away from a serious pandemic. And it highlights the importance of studying infectious diseases. And the current pandemic we're facing kind of corroborates whatever the core of this message. So our group has been looking at the different ways our different expertise can play a role in our project. Granted that most of us are very new in this field of modeling infectious diseases. Next slide. So I want to just share some statistics on some recorded human pandemics. You can see that these are all huge numbers and they don't go away magically. They need work from infectious disease experts and modelers like mathematicians. So there's need for mathematics. For instance, the smallpox or the 1918 and 1919 flu pandemic killed more than 50 million people. And we don't know where COVID is going as of the moment. So we need every hand on deck on that. Next slide, please.
So here, can you hear me? So here we're comparing recent coronaviruses that have impacted humans, starting on the far left here with the severe acute respiratory syndrome of 2002. And then in the middle, we have the Middle Eastern respiratory syndrome started in 2012. And then of course, on the far right is our present pandemic, COVID. So coronavirus identified in 2019, or otherwise known as a severe acute respiratory syndrome number 2. Right? Now, we want to highlight here the stark differences between our present pandemic and what we've had before. You can see the numbers are quite drastically different, even if we just consider USA to the impact of the other two. Right? And also in this last row, we can see the strong influence, the impact of this globalization. Right? COVID-19 is in every country, as opposed to the other two, which were considerably less. Okay, next slide. So coronaviruses are a group of viruses that cause diseases in mammals and birds. And it's believed that they become human coronaviruses. Those human coronaviruses originate in bats and rodents. So with the three that I've talked about in the previous slide, MERS, the SARS-1 and SARS-2, which is COVID 2019, the origin is with bats, and the intermediate host are these three animals here. The MERS, Middle Eastern respiratory syndrome, the intermediate host is a camel. And with SARS-1, it was the civet cat, which is a wild cat. It's not a domestic cat, it's a wild cat. And then the COVID 2019, it's believed the intermediate host is the pangolin. So the other very challenging feature of COVID 2019, I'm sure you've heard, is how very transmittable this particular coronavirus is, right? And transmission is believed to be, just direct contact with contaminated objects and the inhalation of respiratory droplets. Okay. Next.
Next one. All right, just a little bit of history on mathematical modeling of infectious diseases. A lot of the work in developing the framework was done by biologists and epidemiologists. Some of the famous ones are Sir Ronald Ross, William Ogilvie-Kamak, which we still use a model that he contributed until today, which is the Kamak-McKendrick model, which we're going to talk about a little bit. It was later on that mathematicians and physicists like Bernoulli ended up contributing immensely into the field. Next slide. All right. When working on mathematical epidemiology, it's also, you can't avoid paying attention to what the public health experts want, what they want to get out of it. And what their wish list include estimation of the reproduction number, R naught, which we've heard a lot about in the news lately, and we're going to talk a little bit more about that, and the qualitative nature of the spread of the disease, and estimating the burden of the disease. How much PPEs should we budget for it? Do we have enough space for hospitalization and ICU admissions? An assessment of control strategies, like how much vaccination do we need to achieve herd immunity, or do we need, how long do we need to lock down, and things like that. Next slide. But then as mathematicians, we have our wish list too, and sometimes it's demanding. And in order to make it go hand in hand with the public health wish list, we need to do a lot of work. And but our main wish lists include characterizing qualitative dynamics of the model we come up with. What kind of bifurcation do we encounter? Deriving conditions for effective disease control and persistence. And then we have to deal with data. How do we collect and process this data? How do we deal with missing data? How do we deal with incomplete data and stuff like that? And then how do we fit data and estimate parameters? And how do we use machine learning techniques to build predictive machine learning models for classifying or clustering based on symptoms, demographics, geography, etc. And then we need to look at how to do efficient high performance computing. And then at the end, our model we need to be able to communicate with the public, starting with the public health officials. So we have to actually worry about designing user-friendly software that that other people could relate with easily. Next slide, please. So far, since about all of us, we have different backgrounds. We've been learning a lot, and we'll be discovering that to continue in this field, we need a lot of mathematical tools. We have to dust off some of the mathematics we've learned, including differential equations, dynamical systems, topology, graph theory, stochastic analysis, real analysis, Bayesian statistics, numerical analysis, deep learning and machine learning, and a whole lot of linear algebra. Next slide. Okay.
Right. So some of the models that we're going to be talking about today, they're really developed by the biologists and epidemiologists. And the question is mainly estimating thresholds, so different types of thresholds that have to do with each system. So one of the important things is the reproduction number, and that is, before we get to the formal definition, how many people an infected person can transmit the disease to. So the reproduction number R naught is going to be in terms of if there's no intervention. So intervention such as a vaccine or mask wearing. RV is a similar reproduction number, but computed, it'll be a completely different number because now we have a vaccine or something that is preventing people from contracting the disease. And some of the other thresholds that we'll be estimating are transmissibility, the seriousness of the disease, and maybe the impact the disease has on the body or in this society. Next. And so we're going to focus on the SIR model, and these are compartmental models, meaning the whole population is split up into different compartments. And so S being susceptible, so the people in the population that can get the disease, the infected, those are that infected, and then recovered, those that have recovered. There's different expansions on this basic SIR model, the SEIRR, and E standing for exposed. So these are people that have been exposed to the disease, but are still in the incubation period, so they might not be infected yet. and then they move to the infected stage. And then the SEIRS model, the very last one, they add in another susceptible stage that is after you are recovered. So we'll focus on the SIR model, and this is, like Lawrence stated, the Kermit-McKendrick model. And so this one is specifically interested in the total number of people that are infected with the contagion, and the population is closed over time. So there are no births or deaths due to the disease, and there's also no deaths due to natural causes, so the population there is fixed. There's an incubation period, so the time at which you are infected and to the time that you become able to pass that infection on to someone else. And then also there's a homogeneous population where there's no age or spatial structures within those compartments. Next. So the system of differential equations looks like the following for the SIR model. We have our S and our I and R states, where the rate at which you go from susceptible to infected is going to be our beta, and gamma is the rate at which you are infected to which you become recovered. So that's our recovery rate. So there are a total population of N. So N is going to be the sum of the people in each individual compartment of this model. And then 1 over gamma is going to be the average time that an individual remains infectious. So how long you can remain infection and meaning to pass on that to other before you recover. And so like Lawrence mentioned, the reproduction number is very important here. And since we just have the basic model, our threshold there is going to be beta times our susceptible population at time 0 divided by gamma. So again, the reproduction number is important because this is the average number of secondary infections that are produced when one infected individual is introduced to the population. So if we look at the picture on the left-hand side, this our R naught in this case is 2. So we have the red are the infected individuals and blue are just susceptible. The difference between the left-hand side and the right-hand side picture, the one on the right has yellow, and this means that we have now introduced a vaccination or some kind of prevention method such as masks. So these yellow individuals may or may not become infected depending on, because they're partially protected. And then we also have the susceptible. So even though the reproduction numbers are the same here, the rate at which you're infected is going to be different for both of these. Next. So in this figure here from the paper at the bottom, Lepon, it summarizes some of the reproduction numbers of the big epidemics that we have seen, or pandemics that we have seen over time. And if we look at the second row on the left, the first one in the second row, this is our COVID-19 currently. And on this paper, they have a reproduction rate of 2.5, but due to newer studies, this is actually at about 3, somewhere between 0 and 5 are the reproduction numbers here, but we're closer to a 3 currently. But we can see how this reproduction rate differs compared to, for instance, measles, which is in the bottom right-hand corner. And so the reproduction number there is 16, meaning that one person can, on average, infect 16 other people. And so this goes through some of these pandemics that we've seen. So in computing the reproduction number, we are interested in the disease-free equilibrium. So this is the point at which there is no infection in the population. And then also the unique endemic equilibrium, which is when the disease cannot be totally eradicated from the population, but it's no longer a pandemic. So we're not in a state of worry or frenzy. So this state is when our reproduction number, R naught, is greater than 1. And so as a consequence, when the reproduction number is less than 1, this is when the disease usually dies out, and it's necessary for control of the disease or complete elimination. Right, so how do we actually compute the reproduction number? And there are three different methods that we've looked at so far this week, and that is inspection. So using the disease for equilibrium, linearization, so again, linear algebra, defining the eigenvalues of the Jacobian. And lastly, the next generation operator method, which here uses the spectral radius to compute the reproduction number.
So with a basic understanding of the COVID virus, we developed a simple modeling framework to investigate the COVID-19 pandemic, starting out with a population of susceptibles, exposed individuals, and those exposed individuals who become infected, or they become asymptomatic, or they self-isolate themselves. So infected individuals will go to a hospital to seek medical attention, and from there they will recover. While in hospital, they might die, or while they're infected, they might also die. Infected individuals could naturally recover and go into a recovered class. Hospitalized individuals might quarantine themselves, and within the quarantine state, they might recover or they might die. And from being asymptomatic, individuals may self-quarantine themselves. And through this schematic diagram of what's taking place at a population level, we have a rate of change of the different classes at a population level, which is defined by the system of differential equations.
And jump in quickly. I think the Q class is supposed to be the people who are
Quarantine.
They're in ICU admission. They're in ICU admission.
Okay.
Yeah, so
quarantine.
People in ICU.
It's include quarantine and
ICU.
No.
It's ICU. ICU admission.
ICU.
Yeah.
Okay. So it's not just quarantine. Okay. Thank you. Anything? I think that's all for this. So the goal for next week is to focus on doing a qualitative analysis of the basic basic model. For example, calculating R0, doing some bifurcation analysis, doing some parameterization and data fitting. So look at the data, what data is out there, and try to fit it to our model so we could make sense and forecast the outcome of the disease in certain parts of the world and the US. Use data from specific scenarios, example Arizona, my mentor's favorite state, and use computer programs to run simulations.
Okay, and so then we also got together and talked about some big questions, right? So not just the ones that we can do next week, but in the years to come. And one key question was what types of bifurcations that occur in COVID-19 transmission dynamics. That is, this R0, this key parameter that we have R0, to understand the qualitative changes in the behavior of the disease as R0 changes. So understanding, can we control the disease if R0 is this value or that value, with the threshold, the key value being around 1, right? With R0 being around 1. Also, we thought maybe it would be interesting to think about how can we prepare for another wave of COVID-19, and how can we inform the public health practitioners and the medical doctors? How can we work together in this very rich, multidisciplinary area and help one another and help deal with this pandemic in the best way? And then another question, I won't read all of these, but the other very interesting question that is key, I think, right now, and that is, are vaccinations enough? Will vaccinations alone be enough to eliminate COVID-19? Right? I'll stop there. I don't know how I'm doing with time, but there are lots of very interesting questions that we are excited to talk about and address, hopefully. Naomi, can you hear me?
Yeah, I can. Great.
Okay.
You're a little bit over, but that's fine.
Oh, sorry. Okay.
That's okay. It's okay.
They've been working so hard on this, like until like 1 in the morning or 2 a.m. And I really think it's a great collaboration. I mean, everybody was very much involved. And they didn't sleep. I don't think they slept last night.
I didn't sleep.
Oh.
But I should clarify one thing they mentioned. Once you're in the E-class, and thank you to Lisa for clarifying, the E-class are people who are newly infected. You're already infected, but you're not infectious. So exposed in mathematical biology language means you already have the disease, but you're not ready for prime time. You're not ready to transmit to the next person. So those are people who got the infection straight away. So if you're in E-class, you already have the disease, but you do not display clinical symptoms of the disease until you go to the I-class or A-class. So at the end of the incubation period, we split them. A proportion goes to the infectious class I with symptoms, and the other proportion goes to the A-class. And that's the major part of COVID-19, because majority of the people who have the disease, who are capable of transmitting, do not even know they have the disease. So that's why this project is so important, because they're going to estimate the size of this class A, or asymptomatically infectious people, using these approaches there. It's a collaboration. I mean, a lot of dynamical systems analysis, linear algebra, and also a lot of statistical uncertainty quantification, data fitting, and all that. So that's what we're going to be doing next week and the weeks after.
I have a question.
Yeah, go ahead.
Yeah, the question is mathematical. The first questions that you guys asked at the end of the slide was, you want to investigate what types of bifurcation occur. So my question is, are you asking the question of existence of bifurcation because you have evidence from data suggesting that bifurcation might occur, or is it because the system of differential equations that you guys are using tells you that there must be some kind of bifurcation?
Well, yeah, so bifurcation means a change in the qualitative behavior of the system as you change a parameter. Mm-hmm. And the key parameter, as Akisha and Sherry, I think I've mentioned, okay, I'm breaking my rule here, but the key parameter is the reproduction number, which is the spectral radius, is the dominant eigenvalue of some next generation operator matrix. As you change that, as you go from 0 to 1, for example, you see one type of dynamic where the disease-free equilibrium is locally asymptotically stable, which means you have a chance, you might be able to control the disease depending on, if you have only a forward bifurcation, which means at R0 equals 1, you have a transition to another equilibrium, which is the equilibrium with disease. So a slight bifurcation to the right of R0 equals 1 takes you to the other branch, which is the endemic equilibrium point. So at R0 equals 1, you automatically always have a bifurcation. Okay, at R0 equals 1, you always have a bifurcation. So a slight bifurcation to the left of 1, you have disease-free situation. Slight bifurcation to the right of 1, you have endemic situation. But you can have different levels of endemicity. You may even have limit cycle behavior, with an isolated closed curve and so on. So typically this model, this Carmack-McKendrick type models do exhibit bifurcations. Okay. The type of bifurcation tells us whether or not we really have a strong chance of controlling it. There are many different types that we studied in differential equation classes, like transcritical bifurcation, which is the one I just described. But you could have a backward bifurcation. And so at the bifurcation point, how do you characterize the type of bifurcation? We have to use advanced techniques like Santa manifold theory, because linearization doesn't tell you what happens at 1, at R0 equals 1, right? Because at that time, linearization works only if all the eigenvalues have negative real part or one has positive real part. But when you have 0 real part, then linearization is thrown out of the window. It doesn't work. So you have to use more advanced machinery, such as the normal form theory or Santa manifold theory, to characterize the direction of bifurcation at that point. So that's what we hope to do. There are many different types. That's pitchfork bifurcation, that's Hawk bifurcation, which is the bifurcation from an endemic equilibrium to a limit cycle. Depending on the types of bifurcations, we can inform public health people what sort of situation they're dealing with. And in fact, actually, many of the public health people we work with, they really understand and appreciate the bifurcation type, particularly the backward bifurcation, because backward bifurcation says when you, the reproduction number is less than 1. I know, time, sorry.
Yeah, I hate to interrupt you because it's so interesting, but I want to be conscious of the time.
Yeah, sorry.
But we have plenty of time to talk offline.
Yeah, all right.
So we should move to the next group. Thank you.